Welcome back to the crystal clear electronics studio. This is the fourth and final video of the revision of basic mathematics series. Szabolcs, what are we going to talk about?
In this video, we will go beyond the basics of mathematics to look at functions and how to represent functions. First, we will review the Cartesian coordinate system, which everyone has learned in school. In engineering practice, it's very hard to create formulas for certain connections often. Therefore, we rather represent them graphically. In a right-angled coordinate system, the most common representing form practically consists of two number lines, which are called axes. We often call the horizontal axis as x-axis, the vertical one as y-axis. In this coordinate system, we can mark points. Every single point has an x and y coordinate which describes exactly the point's location in the coordinate system. In the figure below, we marked point A, whose x coordinate is readable here. Suppose that somebody gives us two golden coins for every single step we do. This could be written down as an equation in the following way. Golden coin equals 2 times the number of steps. So, as you don't want to write down the expressions golden coin and number of steps every single time, let's use letters as markings. Instead of x and y, we could have used other characters as well. Such expressions are usually called functions. In this example, y depends on x. Usually, this connection is marked by this sign. In a Cartesian, or perpendicular coordinate system, the relation looks like this. The graphical representation can be imagined as the following. If we substitute the horizontal axis values one by one onto the x, we get a y value for every single x value. Then, we represent the coherent xy pairs in the coordinate system with a single point. For example, when x equals 1, then y equals 2 times 1, which equals 2, which is point A. When x equals 0, then y equals 2 times 0 equals 0, which is point B. If we take all the points, then the full function can be drawn.
So we can map a real-world problem into a mathematical function. We can use it better later when calculating in the microcontroller that we will program later in the course. For example, we could plot the state of charge of a battery cell from a 0 to 100% on the x-axis and the corresponding voltage on the y-axis.
That's right.
But that's not a linear function.
That's right. Not every function is linear. Although I don't know what kind of function this is, but it's definitely not a linear function. Let's move on. Now let's deal with angle functions. An angle can be usually given in two different units, in degrees and in radians. The symbol of a degree is a degree character. The angle of a full circle is 360 degrees. The symbol of radians is rad in brackets. Angle of a full circle, measuring it in radians, is 2 pi. Out of this information, the value of a radian can be calculated in degrees, which is circa 57.3 degrees. The knowledge of trigonometric functions is considered to be known in right-angled triangles, and we'll go over the method for defining sine and cosine functions for angles greater than 90 degrees, i.e. angles greater than pi over 2 radians. During the definition of trigonometric functions, the so-called unit circle is a great help for us. Its radius is 1 unit long, drawn in the origin of the usual Cartesian or perpendicular coordinate system. Take a line, which has a phi angle measured from the positive side of the x-axis. According to the definition, the coordinates of the intersection point between the line and the unit circle are cosine phi and sine phi. In the following, we consider these as the definitions of the sine and cosine functions. It's visible that for angles phi less than or equal to pi over 2, this definition is the same as in primary trigonometry. Because the hypotenuse, the side opposite the right angle of the right-angled triangle, is unit long, the length of the legs are just sinus phi and cosine phi. Advantage of the definition is that we visibly get functions that are interpreted for any real number. The introduced sine and cosine functions are periodic. In common sense, a finite section is repeated. More precisely, it's true for them that it is possible to find a p greater than 0 real number, of which it's true that f of phi plus p equals f of phi. The smallest p number like this is called the period of the function. This value for the sine and cosine functions is p equals 2 pi. The square, triangle, and the sawtooth waves are periodic functions which occur often in electronic applications as different waveforms. They're hard to describe with an equation, while it is easy to represent them graphically. We frequently use the sine and cosine functions for modeling any function that is periodic and changes over time. If we consider the time as variable, then the primary transformations of these functions can be given generally in the following shape. In this form, the a sub o is a shift to the positive direction of the vertical axis, which is called the mean value in applications. The a multiplier, which is an a-long provision on the vertical axis, is the amplitude of the signal. The phi 0, which is a shift to the negative direction of the horizontal axis with the value of phi 0, is the phase of the function. The omega parameter, which stretches or shrinks in the direction of the horizontal axis, is called angular frequency. As it was introduced in the previous part, the sine phi function is a periodic with a period of p equals 2 pi. Now let's see what the upper function's periods are, i.e. the periods depend on the t variable. Mark this with a capital T. Write the value of the function at the capital T and at the original location. If we subtract a0 from both values, then divide by a, we get a simple formula. Always treat the brackets as a gift, so we expand the brackets. We end up with a periodic time of 2 pi over omega. We think, in agreement with the author, that this amount of mathematics repetition should be enough for the rest of the course, for designing circuits and programming them. I wish everyone good luck.
Honestly, I also needed a little repetition. Thank you very much. It will be very useful in the future. This was the fourth and final video in the first chapter of the Crystal Clear Electronics curriculum, Revision of Basic Mathematics. Mr. Szabolcs Pájer, I would also like to thank you for your recent lectures and for the dedicated work you do with the students in the secondary school. At the end of the video, we have another service announcement. The curriculum can be downloaded in PDF format from crystalclearelectronics.eu and in Hungarian from kristálytisztaelektronika.hu. You can find the mobile app for Android and iOS platforms under the same name. You can also follow us on Facebook, where you will be informed about the following videos.
Sziasztok!